Hello ladies and gentlemen, and welcome back to what's going to be the second lab for GGS 300, Quantitative Methods for Spatial Science. And today what we're going to be going over is actually working out how to calculate some of those descriptive statistics that we covered already within the lecture. So we're talking about measures of central tendency, measures of dispersion, and measures of distributional shape. Okay, and there'll be a couple of other things which I've thrown in to show you. So things like how to actually develop your own and use R functions, and also a little bit of an explanation about why we use the number of degrees of freedom when we are actually, for example, trying to estimate the standard deviation from a sample rather than from the population. I'll demonstrate using a little bit of code how that actually plays out when you use one or another metric. Okay. Great, so hopefully you'll be able to download the second lab R code from the MyMason Blackboard website, and then you'll be able to load it up just like I've got here and follow it along with me. I'm going to start by basically using an inbuilt data set, okay? And this inbuilt data set is called Faithful, and that data set basically represents the waiting time between eruptions and the duration of the eruption for the Old Faithful geyser, which is in Yellowstone National Park. Okay, so I wasn't particularly familiar with what this was when I first came across it. So as a consequence, I basically had to Google it, so I'm going to show you here. Many of you probably already know what this is, but I just wanted to make sure that it was all clear in your mind. Okay, so I think that there's some sort of geological feature under the ground, and essentially the geyser spouts this water up from beneath it, so it's kind of hot water, I think. And then occasionally, you know, the eruption will take place like this, and there's a certain waiting time. And basically, what we have is the statistical data set which underlies this kind of natural phenomenon, which is pretty cool. I haven't made it up to Yellowstone yet, so hopefully at some point. Okay, great. So you can just load the data set by, for example, just running Faithful as I've done here. Remember, I'm just pressing Control-Enter in order to execute that. You could just click Run up here. You've now submitted an assignment, so I know that you must have a working command of R at least, which is good. So I'm going to probably focus less on, you know, the nuts and bolts as to how you use the software as maybe I did in the previous session, and we're going to be talking more about now how we kind of generate those statistics. Okay. So look, we've got the data set just here. What we're able to do is we're able to just get the number of eruptions. I think that's what this is. So eruptions here, this metric is, it's the eruption time, okay, in minutes. So my bad. So these are all the number of minutes that the eruption took place for, okay. So we can allocate that into our global environment here as this X value, and you can see it's 3.6 minutes, 1.8 minutes, 3.33 minutes. And actually we can sort them like this. So for example, if you want to find the mode, which you know we covered in the lecture, it's the most frequently occurring value. If you want to find the mode, you could just sort them and try and do them manually. Try and do that manually, so you can see 3.833 seems to come up a lot. But I wouldn't advise that, because we're here to use computers, and obviously computers are able to automate all the boring things that you don't want to have to do manually. So it's worthwhile, taking a more advanced approach to this. What we could do is we could just plot a histogram as we've done here, okay? So this is just a histogram using the inbuilt number of buckets. We're not specifying any here, we're just using the hist function, which I know you must have used previously. Or we could say we want 20 buckets, essentially 20 bins, and that's what it's produced here, okay? And you can kind of see that we've got these two peaks, so around just below 2, and just on 4.5, okay? So this is kind of giving us some indication as to where the mode, or modes in this case, may be, because it looks like it's bimodal. So I was going to ask you to describe the characteristics of the distribution, but I've kind of just done it for you by explaining that it's bimodal. Hopefully you kind of got that, but obviously this looks like two quite specific different peaks in the data and then quite a big gap in the middle here, which is interesting. I'm not sure why that happens. Okay, so we can make our own mode function, which basically is a nicer way to kind of calculate the mode, okay, to do it automatically. So what we're doing here in R is by saying we want to specify our own function, okay, and the function is going to be called myMode, so that's what we're going to allocate it to, and it's going to have one argument, which is the DS here, so it's the data set. And then essentially we're going to open it with a curly bracket and close it with a curly bracket, and then everything inside here, it will just operate over using the data set that you provide it. So it's going to create this as a vector and then create a table out of it to get this z value, and then all it's doing here is saying find me return the value basically, which is the maximum in the data set, okay, the most frequently occurring. And what it's done here is it's said, well, okay, the most frequently occurring value is 1.867 and 4.5. So for the computer scientists among you, you'll be aware that these are being returned as strings, so character information, so basically how you would refer to words, even though they are numeric. But really what's happened here is it's been transferred from numerical information into this kind of character-based information. As I mentioned before, this is like the mode is a good way to represent categorical information. So it's basically treating them like categories and returning the most frequently occurring, okay? So look, I don't want to dwell too much on that because it's fairly simple, okay? So let's get started on the median, because we covered quite a bit of ground on the median in the lecture. So we know that this is going to represent the middle point in the data set where 50% of the values are above and 50% of the values are below, okay? Which means that we need to sort the data set first. So for a data set with an odd number of elements, we can find the position by just taking the number of entities in the data set and dividing by 2 and finding that index value. That's fairly straightforward, so we can just round up to the nearest integer to find that. Or for a data set with an even number of elements, it's going to be a little bit more complicated because we have to find the middle two data points basically and then average between them, all right? So let's do that. First of all, let's find the length, so the number of observations in the data set. So this length function just says we have 272 observations in our x numerical vector here, which is the eruption time for the old geyser. Before using these formulae, we want to sort the data set. Okay, so what we've done there is we've just sorted x and allocated back to in the environment. So you'll see now it's slightly changed. It's 1.6, 1.67, 1.7. Okay, and this then allows us basically to say, okay, I want you to index into that data set. So when I go x and I go square bracket, we're going to refer to a position within all of those rows. So you know we've got 272 rows. If I just said go to row 1, it's going to return the item that's at row 1. Okay, so you see 1.6 was returned here. Can you see 1.7 there on the right hand side is on the third row? I could put x square bracket 3 and it will return 1.7. So it's just saying go to the third row and return to me that value. Okay. So what we're doing here is just saying get the total number of data points that we have in the data set, which is 272, divide that by 2, and then that's just going to be the index that we asked for it to return. Okay. So if we do that, the position 1 that's going to be returned is the value 4, and the position 2 that's going to be returned is the value 4 as well. So 4 minutes for both of those, which makes it relatively easy. But essentially, we could add them together as the numerator and then divide by 2 in order to get the average, and obviously that's going to be 4. We could string this together into a huge one-liner, which is very common, particularly in Python or R. You can create these huge one-liners, which is fine. It just makes it harder for people to follow. There's no problem with you doing this, providing you understand what's going on, but it's generally easier to kind of break the problem down. So it's a little bit like when you're starting out in math and your teacher explains that this is how you should kind of formulate your working, and you don't want to put too much working on a single line, so that then when someone's actually reading it, they can understand what's happening in a very clear way, because obviously you get marks for your working out. Okay, and what you're going to do in your homework, aren't you, is that in the assignment you'll just use the standard median function. Okay, so I've gone to all of the hassle of writing this out here, but you can just literally go, give me the median for this data set X, and remove any values that we have which are not suitable. Okay, so not so they're basically NA values. So let's check what that stands for. NA. Not available values. Sorry, I kept meaning to say not applicable, and that is not the correct acronym. So not available values. So if you had a vector of numerical information, you had one qualitative piece of information in there, it would say that that's an NA value, basically. So you want to remove those. As we've done here, we said NA equals true. Okay, so I will explain more about that later. It just provides us with a bit of additional functionality. Look, that's got you the mean. Now let's try and get the arithmetic. Sorry, that's got the median. Now let's try and get the arithmetic mean. So what we're going to do is we're going to use the sequence function. So you probably will remember that I explained previously that we could use a number followed by a colon, and then basically another number, and it would give us the string of numbers across there. And then if we use this C, it would concatenate them together. So if we go 1 to 10, we get all of the numbers between 1 to 10, and we can then concatenate them and allocate them to the vector y. Okay, so let me just clear the environment here, allocate y in, so that's nice and clear. We can get the length of the data set n. Okay, so now we've got all of y and we've got n, and we want to find the mean. Okay, so there's lots of different ways that you could find the mean. You could add up individually each of the numbers between 1 and 10 to get the numerator, which would be 55, and then divide it by n, the number of data points which we've got, which is going to be 10, which would give you 5.5 as the mean. Okay. Or what you could do, because there's lots of different ways in R to calculate the metric of interest to you. So I was going to say that the catchphrase some people might say is there's lots of different ways to skin a cat, which is kind of funny. So you can do it here where you use the inbuilt sum function to sum that y vector that we already put into our environment over here. Again, that gives us 55, and then we can divide by n. So 5.5 as the arithmetic mean for that data set. Okay, nice and simple. And then finally, you could, as you might want to use for the assignment for the homework, use the inbuilt mean function. Okay, so what you're doing there is you're just saying type mean as the function, and then you're going for an open bracket, and then you give it the data that you want to actually use, which is this y vector that we've got in the environment. And you can even say, if you've got non-available data points, you can say remove them please equals true, and that will give you a mean of 5.5. Okay, so there's three different ways there. Three different ways that I've shown you that we can produce this same value, okay, using R. There is a different method of calculating a weighted mean. So suppose we have a monthly average, suppose we have monthly averages for summer temperatures, but we want to calculate what the daily average may be. Well, we can't just average across the monthly averages, because the months will have different number of days. I mean, you kind of get a similar kind of average, but as you move to more and more complex data sets and larger models, you want to make sure that you're calculating this correctly. So I'll use a very simple example here, but the problem starts to scale as you introduce complexity. So let's say that we have temperatures, and this is for winter and spring months, so February, March, April, May. So it's 50, 60, 70, and 80 degrees Fahrenheit, so just hypothetical values we've used here. on average, and we've used the number of days for each of those months, so February 28, 31 for March, 30 for April, and 31 for May. So temp and days. Let me clear this. So temperature and days. So we can calculate this by hand by basically summing all of the values in temps and temperatures by the number of days that month, and that gives you the numerator, which is 7,840, and then we divide by the sum of the days. Okay, so what we'd end up with is 65.33 is the weighted average per day. Okay, if that's what we were interested in trying to obtain. So we could do it a different way. We could use the weighted.mean function. So this is an inbuilt function. As ever, if you're interested in learning more about it, you just type help weighted mean. It'll produce over here exactly a description of what the function does. And we can just provide it with the temperatures and the days, and basically what WM2 produces here again is 65.33 for the weighted mean, all right? And just to prove that you couldn't actually simply average the monthly averages, if we did mean the mean function on the temperatures, we would end up with 65. Okay, so not much difference. If you were rounding to the nearest integer, it would just round correctly anyway. But the problem is that this is very simplified. If you had a much larger data set, this could produce incorrect results, and therefore you just want to be aware that you need to take a weighted average if you don't have all of the underlying data. Okay, great. So let's talk a little bit about this missing data part, because I raised it before. What is this NA thing that we have in some of the functions? Okay, so the data set may have the ability for you to decide what to do with NA, and the NAs refer to not available values. So R will not skip the missing elements unless you tell it to do so. Okay, so that's why we were saying before NA.remove RM equals true. That's basically saying if you encounter a not available value, then skip it. Okay, so you actually need to instruct R to do that, as I've already explained. So let's see what happens. So here we have a vector, and that vector, let me just clear the environment here. And that vector, it has largely numerical information except for one not available data point. So if we take the mean here, because it has an NA in, it's not going to be able to process that because you haven't told it what to do with it. So you have to actually tell it that you want to remove that NA value. NA equals true, NA.RM equals true, and then it will remove it and it will calculate the mean just on the remaining data values, so 2, 5, 6, 1, and 6. Okay. So the exception to the rule is that although that not available value is not a numerical value, it is still an item within that vector, which means that if you take the length is actually still 6, which is the total number of data points that we have, unless you click length na.omit, it will include that value. Okay, so all we've done here instead is we've said, can you omit the not available values within our vector and then take the length. Okay, so it's kind of getting rid of that data point. We didn't want the NA, which is up here, and then calculating the length on the remaining values in the vector. Okay, measures of dispersion and availability. So that was the first kind of single measures of central tendency that we've covered now. But now we want to get onto the kind of dispersion aspect and the variability aspect. So we mentioned before that we could take the range, and you've probably encountered that before. So we could take the range for the values for all of the eruption times. So the minimum eruption time we had was 1.6 minutes and the maximum was 5.1. So we could use this high and low value in order to calculate the statistical range, which would be something like 3.5. Okay. And we could do the same if we use the range function. However, the range function doesn't actually return the exact range, it just returns the lower and the maximum. So you need to do a little bit more work in order to access these. So when that range produces this first value here and the second value here, you can index into what it returns in order to get the specific values. So if I go range, and I'm going to use a curly bracket to give it the data set x, and then I'm going to use a square bracket. Remember we covered this previously, where it then allows you to index into that data structure. And here I want you basically saying give me the first value that you're returning, which is 1.6. And here I'm saying give me the second value that you're returning, which is 5.1. And therefore, when you subtract this first value from the second value, you get the 3.5 value, which matches up with how we were doing it before when we were just subtracting the high and the low. Okay. So that's dead easy. We know that the range doesn't really give us that much information. Okay. In which case, let's look at quantiles. We like quantiles because they allow us to segment all of those different data variables into lots of different ways. So let's look at the sequence function within this, because we quite like being able to give specific sequences between 0 and 1 in order to specify our quantiles. So I just need to recap on what that means before we begin, okay? So sec is the sequence generator, and we might already have encountered this, and if you haven't, I just wanted to recap that you can give the sequence generator two numbers, say between 0 and 30, and what it's going to do is it's going to give you a sequence of all the numbers between those values, and it's going to return them here as integers, so whole numbers, in order for you to kind of access that sequence, okay? You could give it a sequence between 0 and 30, and then you could put a third value in there, which gives you the step count, okay? So I've set up here the sequence is the start, the end, and the by, okay? So I'm saying start at 0, run up to 30, end at 30, but I want you to do it by 10 unit increments, okay? So when I do that, we get 0, 10, 20, and 30. So you can see we start at 0, we end at 30, and we go in 10 increments, okay? And you can do the same if you say, okay, I want to start at 30, and I want to go down to 0 in -5 unit differences, so 30, 25, 20, so on and so forth. Right, now you understand the sequence function, we're able to use the quantile function. And the quantile function will take the data that we're going to give it, like x, and then basically if we say that we're going to sequence between 0 and 1 every 0.25 increments, it's going to give us quartiles, okay, because we're going to get 4 sets of data being returned across that x x data that we have. Okay, so here's the quartile ranges. So it runs from the bottom all the way to the top. So from 1.6, the bottom of the range, all the way up to the top of the range. We have the mean value here, so the median value here, and then we have the quartile, the other quartile points. Okay, at the 25% and the 75% value, so the interquartile range parts. We can also do that, as I like, in deciles. So we can say between 0 and 1, give me an increment every 0.1. So that's going to give us 10 increments. So we end up with our deciles here. Or we could say we want to go every 0.2 increments. Okay, so that would give us 5 individual, in this case, quintiles that it returns. Okay, so you can see 0, 20%, 40%, 60%, 80%, 100%. Great, that should be nice and easy, okay? So we can get a summary of all of that data, whoops, by using summary. Yeah, there we go, sorry. That was my typo mistake. So if I run summary like I have done here, you can get a summary and it's going to give us the minimum value, the first quartile, the median, the mean, the third quartile, and the maximum value, okay? And we can even index into this. So if I say I want to go to the 4th index slot, it should give me the mean, which is 3.48. So let's try that, and we get the mean at 3.48. We can even make a box plot out of our x data. So here what we've got is the median here, this black line, and then we've got the interquartile range here. So you can see this data is quite skewed in reality. For the bottom 25% here, the top 25% here, and then they've got 50% within this box here. So that upper 25% is between the thick black line and the top of the box, and the bottom the middle bottom 25% is in this space here, so just below the line before the edge of the box. I like box plots. I think they're good, so make sure you know how to plot one. Let's move on to the standard deviation. So the standard deviation we know already is the average variation around the mean within our distribution. So the way that we need to do that, and obviously you can look along with the lecture slides and all of the equations that are in there. You can look at the equations for how we calculate this. Okay, so I can actually show you that now if you want. So let's go and find the standard deviation. Here we go. So the standard deviation, we need to find it's the sum of the squared deviations as the numerator, the number of degrees of freedom as the denominator, and then we take the square root of it. Okay, and that's for the sample. So this is for the sample. Here we can get the mean first, so this x bar value, by basically saying give me the mean for all of the data in x, and put it into our environment. Great, that's done. We can then get the length, so this n value down here, we can say give me the length of the vector which contains the data points, which is x, and that will be 272. Great, that makes sense. And then what we'll do is for when we run this bracket here, it's basically going to say for every single data item in x, I want you to subtract x bar, so the mean from it. And then once we've got that, what I'd like you to do is I'd like you to square all of those data points. And then once we've got that, I'd like you to sum them. Okay, and then once we've got that, we can divide by the number of degrees of freedom and take the square root. Okay, so this provides us with 1.141371 as the standard deviation for this data. Okay, great. So I did create a little example just in case that wasn't entirely clear to you. So if we say we had these first values here, so it's 3.6, 1.8, 3.33, 2.28. Imagine this is the xi, the x variable that I just mentioned. What the I refers to, therefore, is the index. So x1 will be this value here, x2 will be this value here, x3 will be this value here. And then we're going to subtract the x bar value, so we know that this x bar here is 3.48, so I put that in already. And then what we're going to do is we're going to subtract, so it's the xi value here, it's going to have the x bar, so the mean for the sample, subtracted from it, and we get all of these values here, and then we can take the squared deviation for each of these values, and then we can basically we can sum them. Okay, so what I've done here is I've summed all of those squared values here, so the sum of the squared deviations, and then I've divided it, just as an example, by 4, because that's the number of sample points that I have here, and then I've taken the square root. Okay, and what I get is 1.03. So I am a little bit off the standard deviation, but obviously there's almost 300 data points in here, so I'm not going to write it out by hand. But I just wanted to show you that's what the structure of the data would look like. Okay, so we're subtracting that mean each time from each one of the data points that we have in the data, and then we're getting the deviation, squaring it, and then that's when we start to sum, divide by the number of degrees of freedom, and then take the square root. Okay, so I just used 4 as the denominator here. You could, if you wanted to, use 4 minus 1. Whoops. Which would produce a fairly similar number. Okay, given that this is a sample, it makes sense to use degrees of freedom here. Okay, great. We're doing good time. So you could just say, thanks for showing me, Ed. It was useful that you showed me how to do all of that, but I'm just going to use the standard deviation inbuilt function, which you are more than welcome to use. So here we have the SD inbuilt function to produce that. The only caveat I provide is that it doesn't use the sample standard deviation. Sorry, it does the sample standard deviation, so it uses the n-1 denominator, which means that if you were going to have population data, you would probably be better off actually specifying your own formula so that you can get the denominator correct. Variance. So the variance is the standard deviation squared. So that's quite easy. So we can just take the S value that we placed in our memory and square it, and we get 1.302728. Okay, we could even use the inbuilt function if we wanted to, and these numbers match up. You'll remember the coefficient of variation because I was explaining that this is basically a relative measure for us to understand the level of variation within a particular data set, and then it allows you to compare that one data set with maybe another one that's measured in a different set of units, for example. Okay, so it allows comparison across multiple different types of values. Now the way that we can calculate that is we can take the standard deviation here, we can divide it by the mean, and that gives us basically the coefficient, alright? So the coefficient is a value between 0 and 1, and that coefficient can be interpreted, if you like, as a percentage, and here you would need to therefore kind of multiply it by 100 in order to get that percentage, which is 32.72483, and this is saying that there's 32.7% variability basically within this data set, and then you could compare it with a different data set to see whether there's higher or lower variation within the distribution of those data points. So before we start looking at kind of the shape and the relative position of different distributions, as I didn't want to calculate all of these by hand, I wanted us to install the moments package basically, because that will enable us to use some of the inbuilt functions. So if you go install.packages and then place moments in apostrophes like this, then essentially you will be able to load that package into the actual memory. Okay. Once you've got it in the memory, you can then start to use that function. So before we do that, let's just run through how we calculate those metrics by hand. Okay, so there's no built-in function in the standard packages for skewness, so we're just going to work on that first. So you'll remember when we were working on skew, we had this equation down here. So what we're going to do is basically take the sum of the deviations which have been cubed to get our numerator. So it's basically exactly the same as what happened here, but this time we would be cubing it in comparison. And our numerator here is minus 167.2544. And then we get the denominator by basically taking the number of observations that we have in our sample. So we can take the length of x and then multiply it by the standard deviation cubed, okay? And that produces 404.4359, okay? So then we can take the numerator and the denominator in order to get our skew metric, and that's minus 0.4135498. So it's negative, which is indicating that we've got a negative skew on the data, okay? So the data points are reaching out towards the left of the distribution, towards the negative part of the number line, essentially. You could use the inbuilt function as well if you wanted to. So 0 minus 0.41 is the answer that we get. There's a slight difference in some of the smaller decimal place figures that we have. Okay, so now let's think a little bit more about the kurtosis. So what we just did there was the skewness. So here we were raising things to the power of 3, cubing them. But also we're interested in understanding the skewness of the distribution, so how flat it is, and we're able to quantitatively assess that. So there's no standard built-in function. I think that's what I should have said before in the last one. There's no inbuilt function, but there are functions that we've got from the moments package, okay? And here we're going to be doing the same thing. So we're going to be subtracting the mean from each one of the x values, and then when we've got those deviations, we raise them this time to the power of 4 and then sum them in order to get the numerator. We can then get the denominator, and again it's the number of samples that we've got multiplied by the standard deviation raised to the power of 4 as the denominator. And then eventually we can get the kurtosis estimate by dividing that numerator by the denominator. So we have 1.488 as the results essentially. So if it's positive, then we have a more peaked appearance. Remember, it's leptokurtic in that place. I think before, when we looked at the level of skew, it was actually quite close to 0, and I don't think if you tested that for significance it would be a significant result. I think that here, as we're getting to quite a high value, this could be quite a significant result that we do have. So it might be significantly different from the normal distribution when I say significant. But anyway, we're not going to formally test it, we're just interested here in understanding the shape of the distribution and how we can quantitatively estimate that and produce some nice single figure metrics essentially. So if we want, we can just use the inbuilt kurtosis function, which produces approximately the same value. Okay, let's move on now. So I know that we already used one function rather quickly earlier on, but I just wanted to use another function here, okay, and give you a bit of a description. So it's really kind of handy if you're scripting and you're doing anything more than twice, then really you'd probably quite like to make a function out of it. And it's normally just a small, very simple operation which you kind of abstract into a structure that allows you to give a couple of values and then return the values with some set processing steps carried out on them. And it's nice because you can then reduce the amount of time that you may need to edit your code. So let's say you needed to change that one calculation in one function. If you had it written 8 times in your code, which you could do, then you would have to change each one of those, and that's really annoying. Whereas if you have a function doing it, then basically you change it once, and that changes the overall use of that function, and also then you can test it nicely. And when I say test, what I mean is you can give it a set dummy example of some data and make sure that it produces exactly the number that you're interested in. And that's important because when you build more complex models or you start doing software engineering, you want to make sure that these processing techniques are actually carrying out as you want. And as you get a bigger and bigger and bigger project, you can run all of these tests, and then you can run them as you make a change to your code base and check that it's all still working as it should. So it's a good way to kind of debug and find problems with your code as quickly as possible. So here we have the skew function which I've produced. So basically we're declaring the name of the function firstly here, and then essentially, well, we're assigning it to this skew name, okay? And we're saying it's going to take a vector, all right? So this is a single numerical vector which we will have the function accept. So it's an argument. And then inside the curly brackets is where all the important stuff happens. So we put the guts of the calculation here. You don't have to indent, but it makes it look nicer as I've written. And basically we can find the numerator and the denominator, and then find the skewness value and have that returned. Okay, so let me put this skew value into the actual memory, which I've done here. So you can see skew has come up as a function, and within that function it tells you exactly what it's doing if you click on it. You can't actually access any of these assignments made in the function. So if I tried to run Numa, it would say Numa not found because it's not in the global environment. It's specific, local, just to this individual function, okay? And now we're able to call that function basically and give it x, so the data that we have, and it spits out the skew factor that we've calculated within it. Okay, so this is a very simple function, and it may look more kind of trouble than it's worth to you now, but it's good to understand how functions work, because in the long run they save you loads of time, hassle and pressure, and it makes it easier to debug your code basically. Okay, so just before I finish this this session today, I just wanted to take 2 minutes to provide you with an example of why we use the number of degrees of freedom. Okay, so it's an example of how we try to reduce bias when we're estimating using samples. Now, I think I just want to start by saying that the number of degrees of freedom is n minus 1 because n is the total number of sample points that you have, and if you remove 1, that's indicative of the number of places that any one data point could be moved within the sample. So if I give you a different example, it might try to help you understand what this concept means. Imagine that you have a soccer team, and the soccer team, you're allocating players onto the field, and you allocate a striker, a defender, a midfielder. So basically you're allocating, you have 11 places to go to. As you allocate the striker and you move back through midfield and then you get to the defence, eventually you're going to have allocated 10 outfield players, and then basically you're going to allocate the final person as the goalkeeper, and that final person as the goalkeeper doesn't have anywhere else to move. There's only one place that person could be allocated to, and that's goalkeeper, and that's because it doesn't have a degree of freedom. Okay, so all of the other players always had at least one other option that they could be allocated to because there were still spaces for them to go to. But that one last goalkeeper didn't, and that's why we have the actual degrees of freedom indicated as n minus 1, because that last position that you allocate doesn't have any degree of freedom. So it's always going to be the number of sample points that you have minus 1. Okay? And this matters in statistical terms, as I'll start to talk about later within the course particularly, but also today. So let's provide you with an example of why n minus 1 reduces the bias when we calculate a metric such as the standard deviation. So let's say that we're sampling from a population. The chances are that your sample will not have some of the extreme values, right? So I said this earlier, I said there's going to be uncertainty introduced into your sample when you're picking particularly smaller samples, because you may not have all of the values that are actually present within the population. So without these extreme values, a calculated standard deviation would be smaller, and therefore it would indicate that there's less dispersion in the data, which isn't true. It's just that you haven't been able to sample all of the extremes. So to make a sample standard deviation more closely resemble the population standard deviation, we divide by a smaller number, so the number of degrees of freedom here, to make the calculation larger, essentially. So let's produce a demo. So let me clear the global environment and say we're going to use the rivers dataset. Now, the rivers dataset is basically the length of major North American rivers. Okay, so this is data given in miles from the USGS, the US Geological Survey. And this dataset represents 141 major rivers in North America, okay? So let's have a look at the length of these rivers first, okay? So this is the number of data entries that we have, and this is the length of them. So you can see most of the rivers in North America are under 1,000 miles, okay? And they fall in these first two buckets. We then have a significant number, maybe 10 or so, which are between 1,000 and 1,500, 1,000 and 1,500 miles, and then a very small number which stretch out into the thousands and thousands of miles. Okay, so this is the Mississippi up here, and then we have a range of others which are also quite significant in their length. So we've got a histogram here, so we understand the distribution of the data. So the function for the standard deviation, SD, curly open bracket, just here, calculates the sample standard deviation. Okay, so we need to do the population standard deviation by hand. So let's calculate the population standard deviation. What we're going to do here is we're going to get the mean for the rivers data set. We're going to subtract it from all of the data points in rivers, and we're going to, when we've got those deviations, we're going to square them, and then we're going to add them up, so we're going to sum them, and that gives us our numerator, which will then divide by the total number of observations in our data set for rivers, and then we'll take the square root. So when we do that, we get 492, which is literally the truth value for our data set, okay, because these are all of the rivers over that certain length, and that's the total number that we have overall. We could just take a random sample of 5 rivers at a time. Okay, so if I go sample, it's going to say go into the rivers data set, which you've given me here, and just select 5 randomly. So you see as I just keep clicking Control Enter across this, it's giving me a different set of 5 values each time, and this is us sampling the data set. Okay, so we can take this sample and we can get the sum of the squared deviations, and we can divide it by the population's standard deviation, and we can get the standard deviation down here. Sorry, we can get the population standard deviation here, which is 774.7965, and we can get the sample standard deviation, which is 866. So these are quite a long way off where we need to be, because we've only taken 5 samples. So basically, the small sample size is producing very biased results at the moment. The real question is what's closer to the population measure. Okay, so let's repeat that a few times. What's funny in this is that the population standard deviation was actually closer to the true value in this case, but it was still miles off, okay, because we had a very skewed data sample. So let's repeat that with 50, and when we do that, we get numbers that are both much closer to the actual standard deviation. And actually what we do have is we have a closer value for the population standard deviation, and we have a little bit of a larger value for the sample standard deviation. But it's still not necessarily fully representative, because we've only taken 1 sample, right? So we need to look at this over 10,000 different samples that we might want to take. So what I'm going to do now is basically create 2 vectors, one for the population, one for the sample. And I'm going to say for a value, for every value from 1 to 10,000, so this is called a loop, go into this function, basically sample the rivers data set for 50 samples, 50 data points, and then allocate, using this function, into my p vector the estimate for the standard deviation for the population, and do the same then for the sample. And then when we do that, and we actually take the mean of each of these, what we end up with for the population is 475, and for the sample 480. Okay, and I think the important thing to remember is that the actual true value is 492. So what we've got here is the sample, which had the n-1, was actually much closer to the true value. Okay, and what was kind of nice was I showed you using either a small data sample or even just the 50 data sample, one-off examples of how you could kind of be lucky and you could kind of get closer using the population measure. Except then when you actually average it over, say, 10,000, it shows here that the best approach is actually to use the number of degrees of freedom, so the n-1. Okay, so I appreciate that's complicated, but I just wanted to kind of specifically explain how it's appropriate for us to use this particular formula, as opposed to just using the blanket population equation on the sample when you may not have all of the extreme measures. Okay, I appreciate that this has been a long practical and that there's quite a bit of information to digest this week, so I'm going to let you go now. We've covered quite good ground. We've basically manually specified all of those different equations that we kind of theoretically examined within the lecture, but we've done it here within the lab environment in R and produced some nice little metrics. I'm going to set the assignment, so you'll be able to use the code here in order to inform your assignment submission. Don't hesitate to reach out to me if you're stuck. Try to enjoy the work. Please have a go at trying to do it early. And I look forward to hearing from you. So ladies and gentlemen, thank you very much for tuning in again. And don't hesitate to reach out to me if you've got any further queries. Thank you. Goodbye.